Hello, everyone, and welcome to this new MLIR open meeting. And today, Fabian is going to lead a discussion on the proposal of his about the infrastructure for target offload for OpenMP GPU. Fabian, take it away.
Sure. Thank you, Maddie. I'm Fabian. I'm a PhD candidate at the University of Delaware. And this is an RFC that I posted a while ago and that I just want to get some more feedback. So first of all, we're going to start with some background because not everyone might be familiar with the current GPU infrastructure for compilation. So if there's any questions at any given point, just ask me. Well, last year we introduced target attributes. Target attributes basically determine how to serialize and compile GPU modules, and you can have options like what is the target chip, what libraries do you want to link to, optimization level, and many other options. So far, upstream we have compilation support for NVIDIA, AMD, and Intel. Intel was recently added back in December or November. Basically, the way it works is that the target attribute has an interface that it is called by the past GPU model to binary that will transform the module into LLVMIR and then compile that module into a final binary. And the idea of creating this infrastructure, it was that we wanted to make it extensible. So there are some caveats that we have right now. So for example, we can have the same GPU model and compile it to different vendors and different architectures, for example, like in this case, but that compilation process requires to hide things away that are particular to a specific vendor. It's part of future work to remove this restriction, but unlike the GPU model to binary pass, GPU binaries can hold objects from any target. So in reality, for once you get to binaries, there's no restrictions on what you can have there. Then the first part was serialization, that is transforming a GPU module into a binary string. Then the next part is embedding. We also introduced what we call offloading attributes, and they determine how to translate binaries and kernel launches into LLVMIR. So on the top, we have an example of, let's say, of the MLIR that we would have at the end of the pipeline. And then at the bottom, it's how that translate into LLVMIR. Currently, what it does is that it creates a string with the binary and a kernel name that then gets used by several runtime calls that first loaded the module, then they get the function from the module, then launch the kernel, and then they unload the module. Right now, upstream, we only have one offloading attribute. It's called select object, and basically what it does is it selects only a single binary in the host model. So you can only embed one binary. And so now we get to the proposal. So the idea is to introduce the offload embedding attribute. I already have PRs for all of these. And And this new offloading attribute would change how things are handled. On the right, we have basically the same example on the top. And then on the bottom, on the listing, we have how the translation looks like. So instead of loading the binaries in kernels every time, what we do is that we register them with a runtime library at program startup. So we use a global constructor that will call this function, that will use a specific runtime function to register this binary descriptor. I don't have the full binary descriptor here because it's too long, but in general, it can hold it can be possible to hold different binaries from different vendors. Also put aliases to variables so they can be referenced on the host module and on the device module. And instead of having to, then when you actually call the kernel, instead of having to load the module and load the kernel name, what you would do is this kernel ID gets registered when the initial registration happens. And then for calling the kernel, you only have to refer to that kernel ID, which is just a pointer. That is only what we care about. So several things become usable once we do this. For example, the CUDA and heap runtimes and the linear OMP target runtime become usable. Right now, well, when I refer to the CUDA runtime, I'm referring to the CUDA runtime and not the CUDA driver. So one benefit of, for example, of using the CUDA runtime is that it provides automatic CUDA context management, and which it could be argued that it is more robust and is also interoperable with the driver. But probably the one that I would care about the most is having the possibility to interact with LeonP target. So this is this change. Basically, it is not that long. It's like 600 lines of code. The heavy lifting of kernel registration and all of that, it is being done by a function that is already on LLVM. So this change, it is the cornerstone of the proposal. And I don't think that it is that controversial, and it allows to have nice things like CUDA runtime support. So now with that, we can move into the idea of OpenMP and GPU target offload. On this proposal, and that is the RFC number, we only care about GPU compilation for OMP target constructs. So for example, things like we have on the listing on the right. At this time, we're not proposing anything radical like getting rid of the OpenMP builder. We only care about being able to compile this code. We do propose, or I do propose to add a new outlining pass for OpenMP target operations. It is a pretty simple pass. It is quite similar to GPU kernel outlining. Basically, you feed it a host module with a target operation, and then that will produce a GPU module embedded on the original MLIR with the function outline and with all the target operations and OpenMP operations outlined with it. main reason that we can do this is that OMP target is isolated from above, so it is quite simple to outline it. Now, the reason I'm interested on doing this is, first of all, we are not testing on the MLR side the OMP dialect. Basically, Flang is the only source of truth that we have right now for testing whether the OMP dialect and the translation of the OMP dialect is happening as it should. Then there's also the fact that we cannot use OMP target offload constructs on GPUs without needing Flang or clang. With this change, which is primarily provided by the offload embedding attribute, we're able to JIT OMP offload code and use, for example, MLIR CPU runner to run that code. And this could lead to more interesting things like, for example, mixing GPU and the OpenMP dialects, which at some point could be interesting to, for example, try to have optimization passes that change a OMP Cindy for maybe a Cindy loop for maybe an intrinsic on the GPU, or maybe start moving certain OpenMP operations to GPU intrinsics. And another benefit that we get is that we can develop the OpenMP dialect independently from Flang or clang, because there's no longer a requirement for having the Flang or clang driver to compile these modules. We can go. This is like a full example of showing that it works. We start with the simple. Can you see my web browser in GitHub?
No, it's still.
Okay, give me a second because apparently I'm not sharing screen. And now?
Now, yes.
Okay, so for example, how do I make it bigger? Oh, there you go. In this case, we start with the simple Fortran program with a simple target construct. We use Flang to generate the host LBMIR. In this case, it is just Flang doing its thing, and this IR doesn't have any. Oh yeah, Guray, you have a question?
Yeah, I have a question. So I can understand the need of, having everything in MLIR so you can run OpenMP without Flang and clang. Yes, that's great. But one thing in OpenMP has a lot of implicit rules, like, implicit data mapping, implicit declare target, all of things needs to be done by someone. And I'm wondering who needs to handle in this case, like Flang is going to handle it, or Clang is going to handle it, or you will do everything in MLIR. We need to have a clear page, clear mechanism for this, because if I have another compiler tomorrow and I want to use MLIR with OpenMP, what I have to do as a new front end.
Okay. Yeah, that is a good question. And right now, there are some things that it needs to be handled by the front end. For example, from the design of the dialect, there's a lot of things that they are already explicit, that there are not that many implicit behaviors. There are some things that will need to be explicit, and that should be handled by the front end responsible for generating this code. So in this case, for example, what I would expect right now as an input for what I'm proposing is this code from something like this code that already has all the information that is lowered into the OpenMP target, the OpenMP dialect. So for example, you were saying about mapping clauses and mapping variables. In this case, the frontend already generated that information, and it says, well, you have to map this variable that it's going to go into the target region. And so the path that I'm proposing, it only outlines that information into the GPU module. So all of those tasks of implicit behavior are responsibility of the frontend right now. And right now, I'm not proposing changing that. So if some other compiler wishes to use OpenMP or this route, they would still need to be responsible for creating all sort of that implicit behavior.
Yeah, I see. I think we need to document this, because here I am seeing the front end is generating implicitly this exit, release, and enter alloc for argument, the second argument. But also there is implicit teams, which is generated by OMP target. It is not here, for example. So not everything is visible in the IR.
Yeah, so that is something that is, yeah, you're right. And that is something that is being currently discussed in a discourse on a different RFC by a different person on how to handle that sort of implicit behaviors. The reason that there's no teams construct here is because if you want to add it, to explicitly add it, you need to create the OMP teams operation. And there's some things that I still need to, so actually this is a great opportunity to say. Let me see if I can open the block node. So right now, if you want to have teams, you have to do something like that, like this. And actually, when I was trying to do this, to test out this approach, what I realized was that right now there's a small bug on the OpenMP IR builder in which you shouldn't be generating these themes, because when you put that operation, it is expecting to use the CPU runtime infrastructure. So there's some work, and actually, for example, if you go to Flang and try to use themes, well, I haven't tried Flang like in 2 weeks. That might have changed. So a couple of weeks ago, if you try to do themes on the front end, it will also fail, because there's currently no way to actually correctly handle themes on the GPU side as of a couple of weeks ago. I don't know if that has changed. There's, and this is part of my point, if we are able to also develop this outside of Flang or Clang and have a more generic design and being able to prototype without requiring those compilers, then these things start becoming manageable. Because yes, ideally in its current form, you would need to also add the teams operation to specify that you are also working with the teams. So that is something that is being currently talked on the OpenMP MLIR dialect design. Right now, I'm only proposing having that possibility of compilation within MLIR. Those getting to have like a full front end support is not something that I'm aiming for, and many of those decisions should be left to the front end. I don't know if you have it. Okay. So yeah, and once basically the pass, again, is pretty simple. It outlines the code, and yeah, you can then use target attributes, in this case, to compile that code and make it runnable. In here, so far I've tested this approach with several codes from that are upstream with Flang from several tests, and they are all verifying correctly. And yeah, so far that is the OpenMP side of this. Many of those questions are actually still that, like I mentioned, are still being debated on how to design, and having this possibility of again compiling without having Flang or Clang would be useful for keep designing the dialect. So now we get to probably the more interesting part that we could get in the future with Johannes Dilford proposed the introduction of LLVM offload runtime. So in this case, the LLVM offload runtime is the starting point is just live-OMP target, but the plans are to transform it into a vendor agnostic runtime API for all GPU constructs and make it like the official LLVM runtime. Currently, there are plans to support NVIDIA, AMD, and Intel. Well, NVIDIA and AMD are already supported on live-OMP target. Intel, from the RFC, there's people showing interest in having also Intel and SQL support there. And this infrastructure from LLVM project Offload would allow many things that are currently not possible, like, for example, multi-vendor flat binaries. So you could compile everything on one time for multiple GPUs, for multiple vendors, ship that binary, and make it runnable from the start. One thing that we don't have currently on MLIR, but we do have it for NVIDIA, is JIT compilation for AMD targets. JIT compilation for AMD targets is already possible with the live-OMP target, so it should be possible on LLVM offload. So this would be nice to have, especially for testing, because currently for testing the AMD integration test, you have to specify the exact match architecture that you're running things into. This would allow not having to do that hard match. And basically, the GPU offloading embedding attribute that is basically the main point of this proposal is that it would be the starting point for supporting the LLVM offload runtime. Which this is, I'm not proposing this right now, but maybe we in the future should consider switching from our GPU vendor wrappers in favor of LLVM offload.
Yeah, just I want to echo your opinion. Yeah, that would be really good, because having multiple runtime just makes no sense. And we have like really small wrappers in MLIR for the GPU vendors. I mean, we are duplicating effort, right? If the LLVM offload runtime can work without overhead, you know, for the CUDA or GPU targets, yeah, I think let's use it. That's a good point.
So are there any questions?
Yeah, I have a comment on previous slide 6, I think it was.
Yeah.
Yes, this one. So if I understand correctly, like in this approach, all the kernels are loaded like in the constructors as the program startup.
Yes. So yeah, go ahead. Sorry.
Yeah, and this can be a problem because first, like at least at Intel, in Intel runtime, like loading SPIR-V blob can be quite expensive operation, and if you have like a lot of kernels, it will be like take a lot of time before code even gets to the actual user program. And the second issue is that, let's say, user can have potentially like 2 versions of kernels, one for, let's say, float 64 arrays and second for float 32. And some devices may not support like float 64. And in this case, attempt to load such kernel will fail, will result in error, and with like no way to handle it in constructors.
Yeah, actually, those are pretty good points. First of all, I'm not proposing getting rid of the current select object mechanism that allows you to basically load them on demand. We would keep them there. For example, I don't think that the LLVM project Offload is going to be ready like in the next couple of months. So it would be like a process over time that we might consider it. But also there are solutions to things like the ones you mentioned. We can add attributes or properties to the runtime and say, hey, this call with this GPU, use this specific kernel. And maybe we could also say to the runtime, don't load all the kernels at program startup, just register them. Load them the first time you use it. That is all things that could be handled at the runtime level without that much overhead.
Okay, yeah. In number MLIR, we followed with this like loading kernels on demand on the first launch, but we don't use currently like this current infrastructure, and we have our own.
Could you repeat?
So, like in our downstream project, we used like approach with loading kernels on demand, when they're first invoked.
But there's nothing here in the IR I see that says that the kernels are loaded initially. They are just registered, meaning like the registering at the beginning is mapping the ID to the blob. That doesn't mean you have to call your driver. That just means that the Atom GPU launch kernel gets an ID and needs to be able to can lazy load the kernel, can lazy load in the driver the kernel at this point. It's an implementation detail of what's behind the API here.
Yeah, I guess we can handle it in like MGP launch kernel itself. But yeah, I just mentioned because in current like runtime CUDA wrappers and others, like there are separate calls like load binary, load module and get kernel. But yeah, it can be handled in the runtime itself.
Which is also costly on CUDA, by the way. Like loading all the kernels into the context is like at this point, all the constants that are in the kernels will be copied to the GPU and this kind of thing. So it's non-trivial. So just to say, I agree with you, Ivan, that
yeah.
Yeah, I mean, it can be handled. And also, again, I'm not proposing removing the old infrastructure. Are there any other questions?
Yeah, I had a question about the outlining, like how that kind of works, and how you know which ops to bring in from. If you look at the target op, there are like a bunch of other operations that may have to be included also to have with the mappings, etc.
So yeah, so the outlining pass basically what it will do is it will first on each function it will search for the target operations. Once those target operations are encountered, since they are isolated from above, they are easy to just simply clone them into a function that is in the GPU model. Now, you have to refer to symbols that may be, for example, declare target. And what I do in that case is then I go through each OMP target operation and go through the region and say, hey, is this symbol already on the GPU module? If it's not on the GPU module, is it declared target? If it's declared target, clone it to the GPU model. If it's not declared target, just emit an error. And I don't know if I'm missing anything that should be copied there, but if it is, I imagine that it should be possible to include it on the pass. Does that answer your question?
Yes, somewhat in the sense. I mean, so when we lower the on target, we have to look at the map ops to be able to create the kernel arcs, right? So yeah. If those operations are in the caller, so to say, of the outline function, then we would have to somehow refer back to this. But
yeah, and actually, for example, in this case, you have map entries, and what I do is that I basically just clone that operation into the GPU module. And I'm a little lazy. And since the kernel, since this function is not really relevant because the LLVM translation, the OpenMP builder is gonna still create another outline function, I just use arguments in the function to have function pointers to those particular elements, so I'm able to map back the map entries.
Thanks. I had another question also about I guess the offload handler. I was looking at so it seems like the offload handler kind of does things that the OpenMP builder is doing as well in the target, like the target info manager. So I was wondering if we are duplicating things, and if there's a way to share the implementations. My concern is if anything changes, then we have to change both.
Yeah, and actually, there's a patch that I have for that because I actually have to stop using the offload entry manager because I needed to emit the entries myself to correctly emit those entries. And what I did, and one of the issues that when I first started trying to compile codes and actually using the Offloading driver, one of the things that I found difficult was that the target entry is being generated by with the location of that entry. And since that location might be hidden away or lost, then it is not actually possible to correctly map, let's say, this target entry to the appropriate target entry on the GPU side. So what I did was adding an explicit target entry info attribute just to be able to say this is an exact match and this is the name that we should use, and stop relying on location attributes that might get dropped. But yes, I agree.
Right. Regarding the, can anyone hear me? Sorry.
Yeah.
Regarding the identification of kernels like across modules, it's been a problem I've been running into as well. And what I thought would be a good solution is to not use the location, obviously, but for example, in the case of Flang, for the front end to encode or like to emit a symbol name, to decide on a symbol name and just attach that symbol name to the OMP target. And then the lowering to MLIR would look at the symbol name and just use that symbol name. And then the front end can decide to emit that symbol name in whatever way it wants to. For now, it could be literally the same thing it does currently, which is like the function name, line name, column name. Yeah, I wonder what other people think about that.
Well, I agree that there should be a more stable mechanism to identify and map entries, because relying on a number that may change is not, and also a file ID that might change is not the best idea. But the problem is that now we are talking about also changing the way that Clang handled the offload entries. And also how LLVM handle those entries, because LLVM will use that information for registering the kernels. So I agree, maybe we should come up with a better approach for uniquely naming the constructs, but yeah. Are there any other questions? I think good eye.
Yeah, I have one. I'm wondering how do you plan to handle host fallback? You know, in OpenMP, if accelerator fails, you have to run on the host.
Yeah, so in this case, I'm not proposing basically changing how things are being handled on the host by the OpenMP MLIR dialect. It's just being able to compile the GPU side. The host fallback, that should be automatically handled by the OMP target operation that remains on the host.
Oh, okay. Yeah, okay. This was I was asking. Thanks. Yeah.
Yeah.
Makes sense.
Are there any other questions? So the only thing that I might say is that we, in this proposal, we have two different things, or two different things that we could push upstream. One is the offload embedding attribute that would enable using the CUDA and HIP and LIOMP target runtimes, which again in the future, we could that would be the starting point for LLVM offload, and also the CUDA runtime also provides some nice features. And then a separate thing that we could push forward, which is adding support. Basically, the only part of this proposal that is OpenMP heavy is adding the target entry info attribute, some minor changes to the OpenMP error builder, and the outlining pass. So I think that we could weigh those two independently. Are there any other questions?
Well, if there's no more question, we can take back the last 15 minutes. But thank you, Fabian, for the work and for the presentation, for taking the time of putting together the slides and explaining all of this. I think it's also a difficult topic to wrap your head around for everyone, this flow of toolchain that involves host and device that doesn't make it easy, and how to embed the device IR and the host IR. It's good to have those slides and be able to visualize that. So thank you for taking the time and for doing the work. Thanks everyone for attending. Feel free to comment on this course or on the pull requests. And we'll see you all next time.
Thank you.